Welcome to Asteroid Day 2020 from the European Space Agency. Hello, I'm science and space journalist Richard Hollingham, currently at home in eastern England. Over the next hour or so, we'll bring you the latest asteroid news and also talk about any potential threat to the Earth. Shortly, we'll be meeting our first guests. They include a meteorite hunting scientist who's been working in Antarctica and one of ESA's asteroid tracking experts. And later, I'll be joined by scientists to talk about a mission to intercept an asteroid and how astronauts might one day land on one of these space rocks. Asteroid Day takes place every year on the 30th of June, and that's the date in 1908 when a giant 40-metre wide rock exploded over a remote area of Siberia. It flattened millions of trees. Fortunately, no one was hurt, but if that happened over a major city, it would destroy it. Well, on that sobering note, and before we meet our first guests, let's find out more about near-Earth asteroids. With me now, virtually at least, Dr. Katie Joy from the University of Manchester, who has been hunting meteorites in Antarctica, and also from ESA, Dr. Detlef Koschny, who's involved in planetary defence. Welcome to you both.
Thanks for having me.
Katie, first of all, can you give us a sense of, just unpick a little bit what an asteroid is and what a meteorite is and what a meteor is, and there's an awful lot of space rocks out there.
There's a lot of terminology as well, and it does get very confusing. So the term asteroid refers more generally to bodies that are found between the orbits of Mars and Jupiter. So these encompass a wide range of different rock types that were formed in the early phases of our solar system's history, so about 4.5 billion years ago. Now, some of these asteroids have got knocked off their orbits between the Mars and Jupiter orbits in the main belt, and get knocked off and kind of travel towards the sun, are gravitationally attractive. And some of those go onto their own stable orbits, some of which are Mars crossing, some of which are Earth crossing, Venus crossing. And for those that are Earth crossing, these are referred to as the near-Earth asteroids. And these are the ones that we have to pay close attention to, and we do an awful lot of monitoring of, that could potentially pose a high risk. Now, many of these asteroid objects are, relatively small, so less than a kilometre, and many are smaller than a metre in size. So the size dependency of these things is quite variable. Now, not all of them clearly hit Earth. Some do. Some just pass by without any worries at all and continue on their relatively stable orbits, kind of slowly migrating towards the sun, where they'll be eventually consumed. But when they do strike Earth's atmosphere, and they travel down through Earth's atmosphere, this is where we refer to them as meteors. And then they become, depending on their size, it could be also referred to as a bolide. And these are the particularly bright events that we see fall as large fireballs. Now, the term meteorite refers to the actual rock fragments that we go...
So sorry to interrupt, but essentially they're the same object. They've just changed their names as they come down through the atmosphere.
Yeah, that's completely right. So meteorite is the rock piece that we get at the end of the day. Now, there's a whole manner of different spectrums as well, where we get dust-sized particles. These are called micrometeorites, so the really small stuff, less than a couple of millimeters in size. And then we also have dust, which actually doesn't come from the asteroid belt, but comes from comet debris, so as Earth passes through comet tails. So it is complex, and I wouldn't get too hung up on all the definitions, but the key thing is that some of this material is very safe in stable orbits, and some is delivered to Earth all the time. We have between about 15,000 and 40,000 tons of space dust delivered to Earth, and probably about 500 meteorites, so actual stones bigger than about 50 grams in size.
So Detlef, the Earth is under this constant bombardment. How worried should we be then?
Well, we should be a bit worried, but only a little bit. I remind you of what happened in February 2013 above the city of Chelyabinsk. About a 20-meter sized object fragmented in the atmosphere, and it did some damage. These kind of objects enter the Earth's atmosphere. Well, say there are few of them every 100 years that would enter the Earth's atmosphere. Now, if this happens over the South Pacific, I wouldn't be worried at all. If it happens over a city, I would. And that's exactly why ESA has a program that deals with monitoring these objects so that we know where they are and when they hit.
Now, Katie, you've not quite been South Pacific, but in Antarctica looking for meteorites. So tell me a little bit about that expedition. It's quite ambitious what you were doing.
Yeah, so we have about 60,000 meteorites that have been recovered and classified in the Earth collection. And these include some that have been found in hot desert environments, so Northwest Africa, Chile, such as the Atacama Desert. So really nice places that preserve the stones really well. But actually, Antarctica is an incredible repository. We have nearly 40,000 of those stones have been found in Antarctica. And that's not because more have fallen in Antarctica. It's just because they're easier to find. So they're preserved a lot better on the ice. They're not disaggregated by rain. There's no trees to kind of have to search through to find them. And typically when a rock comes down through the atmosphere, it gets burnt a little bit and forms a black crust. And a black rock sitting on white ice is quite easy to spot, really. And there's also a special concentration mechanism whereby meteorites, the stones fall all over Antarctica, but then they're transported through the ice, and we can go to certain mountain ranges where the ice sort of backs up very slowly behind these mountain ranges, concentrating the numbers of stones we find. So it's quite easy to go and search and find hundreds, sometimes even thousands within just a few kilometre square area.
But there's as much chance as one falling here in the UK or where Detlef is in Germany as there is in Antarctica.
So we think there's actually a slightly higher chance of things falling around the equator. So there is it's been shown in a relatively recent study, and using some of the data from the Fireball network that exists, and also actually using the Antarctic meteorite populations to try and model this effect, we think there's a slightly higher risk to equatorial latitudes than there is to the polar latitudes. Not very much, but a very small one.
And what was that like in Antarctica when you're going across the ice and you spot one of these things? Or are they that easy to spot? I mean, is it obvious?
It's so much fun. It's very cold. I mean, you have to wear a lot of protective equipment to keep you safe and warm. The way we search is we mostly drive around on skidoos, so snowmobiles, up and down the ice sheets. Sometimes we get in search on foot as well, which means you have to wear special crampons so you don't slip over. It's quite embarrassing. You spend quite a bit of time on your rear end, sitting on the ice, staring up, thinking, "How did I get here?" But it's just so exciting. You know, it's a real discovery activity. And so as you drive around, you turn your head side to side slowly, and you spot black rocks, and then you call everybody over on your team, and you all kind of collect the sample at the same time. And it's just the best thing in the world. I can't describe how much fun it is to actually do this. And every time you find a new meteorite, you know, all these thoughts go through your head. What type is it? Where did it come from? When did it get here? What's it going to tell me and other scientists about our solar system's history? So, yes, I've been lucky enough to go on 2 expeditions with our American colleagues, and then we've done 2 UK-led expeditions. But scientists from all over the world who have programs go, so people from Belgium, people from Japan, China, it's a real international effort, and may it continue for a long time, because every time we find a new stone, it could tell us something completely new about an asteroid we've never been to before. We didn't even know it existed, or about the Moon and Mars.
And Detlef, that's sort of the point, isn't it? It's about the science, what we can learn from these things, as much as it is about planetary defense.
Yes, indeed. I mean, the fun stuff about asteroids is they can be bad, but normally they're good, which is what Katie was describing. That for science, they are a window in the formation of the solar system, because that's when they formed. They were leftovers, so to say, from the formation of the solar system. And so there's, I mean, I'm a scientist by education, and now I have to say defend our planet from these objects. So I'm always a bit torn back and forth. But it's, as Katie says, it's just a lot of fun working with these objects.
And Katie, you said that these could come from the Moon or Mars or elsewhere. How do you know where they come from?
Yeah, that's a really good question. So Moon and Mars are relatively easy. So the lunar meteorites, the first one was actually collected in 1979, and then later one in 1981. And these were recognized as being chemically similar to the Apollo samples. So that was a really nice connection. We know they come from the Moon. Mars is a little bit more complex. There were some arguments in the 1980s about whether we could actually get things removed from Mars. So a large asteroid or comet must have come onto Mars's surface, create enough energy to liberate material above Mars's escape velocity, get it all the way off, and then travel here to Earth. And some people argued that this couldn't be done. But actually, in the end, it was some geochemists that were looking at the gas chemistry of the Martian meteorites, and they compared this to the composition of Mars's atmosphere measured from orbit. And this was recently proven again by the Mars Curiosity rover. And this chemical affinity, this isotopic match between the gases in the rock and the gases in Mars's atmosphere, proves this connection unambiguously. So we know that they've come from Mars. Now, where our bodies come from the asteroid belt is a little bit more complicated, because we've only been to a very few asteroids with our space missions. But there's some very clever people that compare the spectroscopic signatures of the asteroidal meteorites we have, and compared that with the reflectance spectrum of different asteroid types.
So essentially, sorry to interrupt, essentially picking apart the chemical composition so you can know exactly what type of chemical it is, and you can match it to its origin.
Yeah, mostly to do with the minerals, the specific minerals within those samples. And we have some very good matches between some meteorite groups and some big asteroids, but others, we've got no idea. You know, there's a complete non-match. And for some of the unique ones, those bodies that created those meteorites might not even exist anymore. They could have existed early on in the solar system and then have been lost either through collision with the sun or thrown out onto different orbits. And so that's why meteorites are so special, because they represent material that may not even exist at the present day in the asteroid belt.
That's extraordinary, isn't it, Detlef? And also, I think it's difficult to get our heads around the fact that they're all moving, the planets are all moving, and we're moving through material as well. It's not like we're static and this stuff's coming towards us.
No, and that's one of the challenges, of course, that again now, if I talk about our planetary defense aspect, you somehow need to predict the orbits of these objects. We compute them 100 years into the future, and we know right now of about 1,000 objects that have a chance of hitting our planet in the next 100 years. But of course, this is all uncertain. It's not easy because of all these perturbations of planets and other effects.
Katie and Detlef, thank you very much for the moment. Very shortly, we will be talking more about efforts to track asteroids, a new mission from the European Space Agency called FlyEye. You're watching Asteroid Day 2020. This is the English language programme from the European Space Agency.
Well, I'm afraid, my old friend, yes it did. It was a very large asteroid, about 10 or 12 kilometers across, and it hit the Earth in the Gulf of Mexico 66 million years ago. And we know this for two reasons. First of all, the debris, the ejecta from that huge impact has been found all around the world, and wherever we find rocks about that age. Secondly, about 30 years ago, geologists found the crater. It's about 180 kilometers across, but you can't see it very clearly now because over the past 66 million years, about a kilometer of rock and sediment have covered it up. But it's there, and we know from modelling and we know from the fossil record that that asteroid was instrumental in saying goodbye to my friend here. The good news is that asteroids that big are easily detected by our modern telescopes, and we know none that size are going to hit us in the next few hundred or even few thousand years.
Let's discuss more about tracking asteroids now, and a new European Space Agency telescope system called FlyEye.
Hi, I'm Kelsey Brennan-Wessels for ESA Web TV. We join you from Milan, Italy at OHB Italia, where a new high-tech telescope to detect asteroids is being built. Let's take a look. This is the FlyEye telescope in production, which isn't what we usually picture a telescope to look like. Traditional telescopes have a narrow field of view, which makes hunting for threatening asteroids a slow and tedious process. But the FlyEye has 16 individual cameras, mimicking the structure of a fly's compound eye, to offer an extra-wide field of view of 44 square degrees. With this field of view, the telescope will be able to detect asteroids at risk of hitting Earth in as little as a week in advance. So, how does it work? Lorenzo Cibin at OHB Italia gave us an up-close look at the machinery.
We can see here the full optical instrument connected to the ground support equipment, and then you can see here the central ring of the instrument that hosts such a lower part is the primary mirror. Kelsey, if you look there is a B-shaper that do a repartition of the field in 16 channels. This is, for example, one channel with the camera, CCD camera, and in this CCD project a portion of the sky.
An additional 3 telescopes are foreseen to be produced and placed in complementary locations around the globe to increase coverage and improve the efficiency of the network. Once this first FlyEye telescope is completed, it is destined for Mount Mufara on the Italian island of Sicily.
Hello, this is Asteroid Day 2020. This is the English language programme from the European Space Agency. I'm Richard Hollingham, and my guests, or virtual guests at least, Katie Joy from the University of Manchester and Detlef Koschny from the European Space Agency. Let's pick up on that, Detlef, in terms of FlyEye. What will it be looking for? It'll be tracking what, the whole sky? I mean, that's quite ambitious, isn't it?
Yeah, indeed. So in order to find out where the asteroids are in our solar system and whether they have the chance to hit our planet, well, you first need to scan the complete night sky. And we came up with a project where we would use ground-based optical telescopes. Of course, that idea is not new. The American colleagues have been doing this for about 20 years. But their efforts are not yet enough. We just need more telescopes because basically you want to look at the complete sky once per night. Right now, with the surveys that we have, we manage to do that maybe every few weeks or so. Now, our so-called FlyEye telescope is a very special design, as the name implies, modeled on the eye of a fly with like multiple cameras behind one optical system to get you a really large field of view. And in the end, we need 3 or 4 telescopes, depending on the weather condition, to really scan the complete night sky once per night with these instruments.
And when you're looking at that sort of telescope, you talk about the whole sky. How far are we talking here? How far out can you see?
We would see a 40-meter sized object roughly 3 weeks before it would hit our planet. Hopefully it doesn't, but let's say before it comes really close to our planet. And 3 weeks warning time is interesting because to evacuate a city, emergency response agencies tell us they would need about a week or 10 days warning time. Now we are a space agency, so we have a factor of 2 margin here, so we get the 3 weeks. And the 40 meters is an interesting number because that's roughly the size of the Tunguska impactor, which exploded in Siberia about 100 years ago.
I like the way you use the word interesting there in terms of 3 weeks. Just before we come back to that and the planetary defence, Katie, I mean, how useful will it be to know just how much there is out there? Do we have an idea really at the moment?
Oh, we do. We do have some monitoring systems, as Detlef discussed, but I think there is this issue about inconsistencies and different telescope, different organisations doing this. So getting a global overview will be a real strength, and it would also be fantastic to make predictions for the risk side of things, which is incredibly important, but also for finding smaller objects that we can see coming, and then we can predict where they may actually drop meteorites. So we could actually go and organise proper systematic search missions to go and recover those samples for science as well. So there's a lot of exciting times ahead for thinking about risk mitigation and science too.
Let's come back though to that thought about planetary defence, because I mean this is the serious end of it, because we know these big objects come near Earth, and we know these big objects, as you mentioned in Siberia, do hit the Earth or at least explode above the Earth, and the consequences are absolutely catastrophic. Do we have an idea of how often these sorts of events have occurred in Earth's history?
For us, the interesting regime is, or the one that we worry about, is the size range of 10 to 40 meters. A 10-meter object would typically happen, say, every few years. 20 meters like Chelyabinsk, that's a few times per century. The 40-meter, like what happened in Tunguska 100 years ago, that would happen every few hundred years. So, and it's statistics, so in principle it can happen tomorrow. We don't have to wait a few hundred years. It's just statistics. And that's the size range that we worry about.
I suppose this has got to be a global effort, hasn't it? I mean, this is a European Space Agency new system, Flyer, but this is global coordination, countries working together, because this is a global issue.
Yeah, just like in the scientific area, I mean, we are relying on working together. And I mean, this is one of the parts I enjoy most when we are at meetings. There are 2 working groups on United Nations level that deal with the asteroid impact. When we have discussions with American colleagues, Chinese, whoever, we are all friends because we talk about the same topic and there is no national issues going on there. And that's actually quite satisfying. Everybody realizes that this has to be an international effort to do something about this.
And Katie, what I love about when you're talking about this is your enthusiasm for these objects. So, we're talking about here, they're potentially a threat if they're big enough, but actually the amount of science we can get from them.
Yeah, it's just incredible. And as Detlef said, it's working with international colleagues to study these samples. So, we can borrow them from different collections that have been recovered around the Earth, and working together collectively, we can tackle really significant questions about our solar system and comparing and contrasting with how other solar systems form and evolve, and fundamentally understanding how the Earth is here and how we've gained our volatiles, our water, and how that could sustain and initiate life. So these are pretty important questions that we can ask these small, relatively unassuming stones, which actually, it's not just an interesting question, but actually have a real effect on understanding who we are and why we're here, and our understanding our place in the solar system and universe.
Now, this is Asteroid Day 2020. Just one final thought from you both. What would be your message for Asteroid Day? Katie, first of all.
I think my message would be we need to understand and explore a lot more, both by understanding objects coming from the asteroid belt to here, but also going out to the asteroid belt and exploring them with new space missions and bringing those rocks back to Earth. So we can learn an awful lot from meteorites, but we can learn an awful lot more by sample return missions. And so that would be my plea, is next time you see a shooting star, maybe make a wish that we could have more space missions to explore this wonderful, diverse place in the asteroid belt.
Detlef.
Well, I would say what you heard us saying all the time, that asteroids are on one hand a threat if they hit our planet, but more importantly, they're very useful for scientists to understand the formation of the solar system. They may have brought water onto our planet and play a significant role in the formation of life. So always think about these two sides of asteroids.
Dr Detlef Koschny from the European Space Agency, Dr Katie Joy from the University of Manchester. Thank you both. This is Richard Hollingham. I'm at home in Eastern England for Asteroid Day 2020. This is the English language programme from the European Space Agency. And coming up, Brian May on the HERA mission to a double asteroid. And could asteroids provide valuable resources for Earth?
The United Nations has long recognized that a potential impact of by an asteroid to our planet, to humanity, can be a global issue. It has therefore negotiated recommendations for an international response to a potential near-Earth object impact threat. These recommendations, that were welcomed by the General Assembly, established two bodies. One is International Asteroid Warning Network, that is coordinated by NASA, and it links together observatories for detecting and tracking asteroids. The other one is Space Mission Planning Advisory Group, which is chaired by European Space Agency. Our Office for Outer Space Affairs works with both in strengthening international collaboration, and this International Asteroid Day, that was proclaimed by General Assembly in 2016, serves as a reminder of this important issue. Stay safe.
Let's have some of the latest asteroid news now. And on the 29th of April 2020, a mountain-sized rock passed close to the Earth, passing 16 times further than the distance between the Earth and the Moon. At 2 kilometres in diameter, the ancient rock rotates once every 4.1 hours. And this was captured in this sped-up video taken by the Arecibo Observatory 11 days before close approach. The good news is, scientists had their eyes on this for decades and knew it posed no risk to the Earth. Well, just a few weeks before that, a new asteroid designated 2020 HS7 became one of the closest flybys ever recorded. It passed just 37,000 kilometres from the Earth's surface and only 1,200 kilometres from the nearest satellite orbiting in the geostationary ring. Our atmosphere would protect us from a small asteroid, but what about the Moon? Well, that's under constant bombardment, and since 2017, ESA's been looking for lunar flashes. That's sudden bright flashes of light when an asteroid hits. And the project, operated by the National Observatory of Athens, recently recorded its 100th impact flash on the Moon, helping us to better understand the threat posed by asteroid impacts in our lunar environment. We're going to talk about missions to asteroids now, and a new ESA mission called HERA, which will operate alongside a NASA mission. And as this is a programme about space rocks, let's hear from a genuine rock star.
HERA is going to show us things no one's ever seen before. This ESA mission will be humanity's first ever spacecraft to visit a double asteroid, Didymos. This asteroid is typical of the thousands that pose an impact risk to our planet. Imagine a mountain in the sky with another rock about the size of the Great Pyramid swinging around it. That's Didymos. And just the seemingly tiny moon would be big enough to destroy a city if it were to collide with the Earth. But we're going to find out if it's possible to deflect it. This is going to be really, really hard. Aiming at a 160-meter wide target across millions of kilometers of void. Could we stop an asteroid hitting planet Earth? The dinosaurs couldn't, but we humans have the benefit of knowledge and science on our side. HERA is led by a multinational team of scientists and engineers, humanity's makers and doers. Right now, all we have is many years of research and theories, but HERA will revolutionize our understanding of asteroids and how to protect ourselves from them. First, NASA will slam its DART spacecraft into the smaller asteroid at more than 6 kilometers a second. Then ESA comes in. HERA will map the impact crater left by DART and measure the asteroid's mass. Knowing this mass is key to determining what's inside and knowing for certain whether we would be able to deflect it. Next come our briefcase-sized CubeSats. If you think of HERA like an aeroplane, then CubeSats will operate more like drones, able to take more risks, flying closer to the asteroid, carrying state-of-the-art science instruments, eventually touching down. The scale of this experiment is huge. One day these results could be crucial for saving our planet. HERA's up-close observations after DART's impact will help prove whether asteroids can be deflected, prove whether this is an effective planetary defense technique, so that if an asteroid ever poses a real threat to Earth, we'll be ready.
I'm joined now by two more live guests for Asteroid Day 2020, Professor Alan Fitzsimmons from Queen's University, Belfast, and Dr Natalie Starkey from the Open University. Hello to you both. Alan, first of all, let's talk about these double asteroids. Are they that common?
Well, yes, they are, and it's surprising to us. It's one of the surprising things that astronomers have found studying near-Earth asteroids. In particular, both radar studies of asteroids very close to us and studies of the light that they reflect, how that changes over time, have shown that about 15% of asteroids near the Earth aren't just single asteroids, but they're binary asteroids, two asteroids orbiting about each other. In fact, we know of a few examples of trinary asteroids, where you've got a primary asteroid and two little moons going about it. And this has been a source of fascination for planetary scientists for several years now, and we think we understand how they form. We think what's happening is that the asteroids spin up under the action of sunlight over time and literally just rip themselves apart and form a double asteroid that way. And it's one of the things we want to test in the next few years.
And Natalie, that just shows the sheer diversity, doesn't it, of these objects?
Yeah, I mean, I think a lot of people learn in, the space science textbooks at school, maybe, that there's very kind of diverse groups. We have comets and we have asteroids. And asteroids are sort of these rocky things that we find in the inner solar system, and comets are these kind of icy, dusty things in the outer solar system. But actually now we've gone out in recent decades exploring these objects just with telescopes and with space missions. We've started to find this huge diversity of objects. It doesn't, nature doesn't fit into these simple boxes that we like to put things into. Actually, there's everything in between. So we have some asteroids that look a little bit like comets. In fact, some have tails as they go towards the sun. And then we have other comets that look a little bit more like asteroids. So there's this kind of blurry ground in between. We definitely have these end member examples of comets and asteroids. But yeah, there's a lot in between that we need to go out and explore to understand a bit better.
And you've been involved in some of these missions to asteroids and comets and other objects. How challenging is that? How difficult is that?
I mean, to approach these things in space can be extremely challenging just to get to them, because if we think about the Rosetta mission, it actually took 10 years for that spacecraft to catch up with that object in space. It had to get onto the same orbit and then do slingshots of planets to build up gravitational energy to actually get enough speed to catch this thing up. But we think about these objects, they're very small. They're not planets. They're not the size of planets with lots of gravity. They're very small, so actually orbiting around them is not a trivial matter. Actually, it's really hard to orbit around them. You have to use powered flight, really, most of the time, to be able to go around the object with an orbiting spacecraft. But then trying to land on them like the Rosetta mission did, and that's the first time we've ever landed on any of these objects, that's extremely difficult because the gravity of that object is so small that spacecraft is not going to be kind of pulled towards it very well. So there was every chance when they released that lander to the surface that it could have missed the object completely and just carried on into space forevermore. So there's a lot of challenges engineering-wise that have to be overcome to kind of explore these objects. But we can do it. We have the technology now, and we're doing it a lot, in fact. Lots of different missions are out there exploring these objects now.
And HERA, Alan, takes it a step further with these multiple spacecraft visiting this double asteroid.
That's right. So HERA, when it gets there, won't be alone. It's carrying two smaller spacecraft with it, things we call CubeSats. And although CubeSats are now quite prevalent in orbit about the Earth, they haven't really been used very much in the past for interplanetary exploration. And so when HERA gets there, it will launch its own two CubeSats. Juventus is one name, and there will be another CubeSat. But these will allow us to investigate this binary asteroid in even greater detail. We've never been to a double asteroid before, at least on purpose. And we are really looking forward to seeing what those probes, the trio of spacecraft combined, can reveal to us about this object, how it formed, how it's evolved over time, and what's going to happen to it in the future.
And this is a planetary defense mission, but also a science mission.
It's primarily a planetary defense mission. It's part of the AIDA project, the Asteroid Impact and Deflection Assessment Mission, which is dual spacecraft, one from NASA, one from ESA. The NASA spacecraft will actually launch before HERA. It will get there in 2022, and it will actually try to move, and I'm sure it will actually move, the moon of our target asteroid Didymos and change its orbit, showing that we can move a small asteroid in the future, should we find one on a projected impact trajectory. But the important thing is that HERA will follow it 4 years later and find out exactly what happened to that asteroid, because that will complete the experiment and show us exactly how effective this technique can be on other asteroids. And that's really important, because we know we don't need to move the moon of Didymos, but we may need to move another asteroid in the future, and that's what we're planning for.
And Natalie, that's the sort of way we might need to protect the Earth, isn't it, as Alan said?
Yeah, definitely. There's lots of different techniques that we think we could use to try and potentially divert an asteroid onto a different course. And really the thing here is that the earlier we know about the object coming towards us, the better, because we have more time to plan and we have more techniques available to us that will allow us to just divert it. If it's really far away from us and we don't have to move it very much, for it to miss the Earth when it gets towards an Earth-crossing orbit, within 10 years. But if we only have a year's notice, we're going to need to do something a bit more drastic, like push it out the way or even explode it or something in order to get it out the way and for us not to collide with the planet.
And I suppose, Alan, you hopefully show that you can move an object, and the further away you are from Earth, if you move an object, you don't have to move it that much, really, do you?
That's right. It's a matter of distance and a matter of time. If we wait like the science fiction movies when you can see it in the sky, then that's too late, basically. You haven't done your job properly. What you need to do is what the surveys are doing now, the upcoming FlyEye telescope from ESA, the currently operating surveys for such as Pan-STARRS and Atlas. What they're doing is finding these objects not only when they're close to the Earth now, but many years before they could potentially hit us. We can calculate their orbits, find out if they're going to come close to us, and then if we try to move it now, we only need to nudge it a small amount so that over time the trajectories diverge, and instead of hitting us, it goes past us. So the important thing, as Natalie is saying, is the time and the distance, and as long as we get it much earlier than we need, then when it's close to our planet, we should be able to move it.
And is this the best, simplest option? Because I'm thinking, we're now thinking Armageddon, Bruce Willis on an asteroid with his mining chums and some sort of atomic device. A little nudge is enough, is it?
Well, we think so. Now, of course, this is why we're doing the experiment. We've never tried to move a small asteroid before. But looking at the available technology, and as Natalie was saying, there's all kinds of ideas that scientists and engineers have come up with over the years. The kinetic impact, basically hitting something fast so it moves, is the simplest technique, although, of course, nothing's simple in space science. You're trying to hit something that's only 180 meters across at 6 kilometers per second, several tens of millions of kilometers away in space. So it's pretty tricky technique to do. But apart from that, then we do have other techniques such as gravity tractors, where we try to gently pull a small asteroid for just using the gravity of a spaceship hovering nearby, and even, as you've mentioned, blast deflection, possibly nuclear, but that really is a last resort. And again, if we have to leave it that long, we possibly should have done the job a little bit better.
Natalie and Alan, thanks for the moment. We'll be discussing the potential of mining asteroids in a few minutes. This is Asteroid Day 2020. I'm Richard Hollingham, and this is the English language programme for the European Space Agency.
Well, the first difficulty you're going to have is actually staying there, because these asteroids are so small, their gravity is so low. And as you walk across the surface, you're going to have to use such gentle steps, because if you push just a little bit too hard, you're going to push yourself off up into space and you're not going to come back. On the surface of an asteroid, it's very easy to lose and to gain weight. These bodies are so small, irregular and lumpy that the gravity isn't the same all over their surface, which means that in some places you're going to be heavier than in others. Bizarrely enough, you might even find yourself in a situation where you feel that gravity is pulling you sideways instead of pulling you downwards. You're going to have to be prepared for all climates, because you can go from temperatures similar to the middle of the Sahara Desert to temperatures like the Arctic winter, and that in just the space of a few hours if this asteroid is spinning fast. However, one nice aspect of asteroids spinning fast is that you're going to be able to see multiple sunsets in the equivalent of one Earth day.
What about mining or exploiting asteroids? Well, it's certainly an idea being pursued by the space agencies. With more, here's ESA astronaut Luca Parmitano.
When humans finally fly to an asteroid, they will need the same skills that they do now. They must be able to use technology to perform science and exploration. However, there is something more. They're going to need some new technology. Initially, we're going to have to be able to find these asteroids, so very precise guidance and navigation. Then we're going to have to park close to an asteroid without hitting it, and that's going to be something that needs to be developed. And thirdly, once the humans need to go on the surface of the asteroid, they're going to need new spacesuits capable of anchoring themselves onto the surface, because such a small gravitational field is going to be very, very hard to explore. So some of the technologies that I just talked about are partially available today. We do have spacesuits, but we must be developing new ones in order to be able to perform the kind of tasks that are going to be necessary for exploration and exploitation of an asteroid. And for the spacecraft, we already have navigation system. We already have, for example, our spacecraft to the International Space Station. But in the future, this new spacecraft will have to be able to do that when connected to a completely unexplored little world like an asteroid. Space is an inherently risky environment, and obviously flying to an asteroid is going to present all the same risks that you have flying in space. And everything that is in the unknown is always an increase in the risk. Today, we are preparing for these missions using analogous environment. One of these environments is called NEMO, the NASA Extreme Environment Mission Operations. It's where we stay underwater in a small environment for 2 weeks in a habitat that's called Aquarius, about 20 meters underwater. When we are in this environment and we stay there for the whole time underwater, we perform the same tasks that we would perform on an asteroid, and we take advantage of the neutral buoyancy of being underwater to simulate the microgravity environment that we would find on an asteroid. Nowadays, when we perform our missions on the International Space Station, it's a very known environment that was designed to be used with handholds and specific places where we can anchor ourselves in order to operate. When we go to an asteroid, we won't have any of those tools. We're going to bring our own and to install them in order to be able to explore and navigate around the asteroid. When we land one day on that asteroid, the lucky person is going to feel something that has never been done before. He's going to be standing on a very, very tiny world with a very small horizon, rotating in the universe. It's going to feel that the whole universe is rotating about you. And I think that that's part of the beauty of it, that we just don't know what it's going to feel like.
European Space Agency astronaut Luca Parmitano. This is Asteroid Day 2020. I'm Richard Hollingham, and I'm still joined by Alan Fitzsimmons from Queen's University, Belfast, and Natalie Starkey from the Open University. Let's talk then about mining asteroids, Natalie. You've written about it in your book here. So how feasible is it?
So yes, I'm going to say it is feasible. The question is just when, really. We have really all the technologies we need to go up and explore asteroids, find out what they're made of, so kind of prospect for them and work out, what's in them and what we could use those materials for. We can actually go to them with spacecraft. What we haven't yet done is fully realise how we can actually get the materials out. So we're talking metals most of the time. A lot of these asteroids, as I've said, are made of iron and other precious metals in huge quantities, and they could be worth, the estimates are ridiculous, like quadrillions of dollars and things. They're worth so much money. The question is not whether we're going to bring them back to Earth necessarily and just flood the market with lots of metals. It might be that these materials could be used to progress technologies on Earth, which would be really useful, but also they could be used in space. So at the moment, we're at the stage of just figuring out how we're going to separate those metals, how we get the gold and the palladium and platinum away from the iron. And if we can do all of that in space, it's not insurmountable. We have a lot of the technologies kind of being investigated at the moment. Then we could actually use these objects for good. And it's going to be a really exciting phase. We might do it robotically. We might even use humans to do it, but that's kind of the stage we're at the moment.
Alan, we talked a little bit about science fiction in terms of knocking asteroids off their course. This very much sounds like science fiction.
That's right, and it is at the moment, let's be completely honest, but if we're ever going to become an interplanetary species and we're going to explore and eventually colonize the solar system, we'll have to not only travel through the asteroid belt, but as Natalie was saying, we'll need to use those resources out there. And right now, we're just at the very earliest stages of using our robotic probes to not only visit these asteroids, but interact with them, taking samples from their surface. But all of this will lead up in the decades, and dare I say it, centuries ahead, to perhaps the first astronaut-led missions to these small bodies.
Natalie, are there valuable resources on there? I mean, we hear a lot about, we're running out of resources on Earth, but I mean, there's still quite a lot here. Is there something valuable there that is worth exploiting?
Yeah, I mean, definitely. These things can be worth a lot of money in terms of the precious metals they contain, but they also have huge quantities of them. So whereas on our planet, our precious metals tend to be dispersed quite finely in seams and different areas, we have to mine a lot of our planet in order to get these materials out. We have to environmentally ruin areas of our own planet to do that, to use all these metals in our smartphones and all the technologies we need them for. Whereas the idea of being able to do this in space is really cool because we can just pop to an asteroid, one that most people didn't even know was there to start with, and it contains possibly all the metals that we need for, decades to come. So it could be that we're actually just going to lose that asteroid, but we didn't know it was there anyway, and then we can use it for our future uses of metals that we need, and we can save our own planet in that respect. So that's what could be quite cool, but obviously there are risks associated with going up and destroying these asteroids. If we get it wrong, we could actually divert one, to crash into our own planet. We've got to think about carefully what we're going to do with these objects and how we're going to bring those materials back to Earth. There's a lot to think about in terms of technology, but they do have the potential to answer some of the questions about our industries in the future on Earth.
Well, let's talk about phase one, if you like, which would be astronauts visiting an asteroid. And I know some, as Luca was talking about, some of the European astronauts have trained for these sorts of missions, have done underwater training for these sorts of missions. What can we learn, Natalie, by sending astronauts rather than just having robotic probes?
Wow, okay, yeah. First of all, robotic probes are always going to be our first option because it's safer. They're expendable. We can build amazing robots on Earth and send them out, and they can do quite a good job of exploring these objects for us. But as we learned with exploring the moon, the best way to explore these objects is by sending humans, because ultimately we're quite clever. We can build great robots, but actually humans on these objects in space themselves are just even better. We can traipse across the surface with an asteroid. That can be tricky. We're going to have to be tethered down because there's not much gravity to hold the astronauts on. But they're going to see things that robots wouldn't have spotted. And obviously we can move around. We have the dexterity to pick things up and look at them in detail. So in terms of rock sampling, it's definitely the best way. It's just like having a geologist out there, like we would have on the Earth exploring our own planet, but we've got them looking out for things on an object in space. And there's huge value in doing that. But obviously it comes with the fact that it's extremely dangerous. It's going to be even, worse than going to somewhere like the moon or Mars. There's a lot more to think about, and it's a very unfriendly environment for these people if they're going to go and explore these objects. And we've all seen Armageddon, as you said. That's very much science fiction, but that's the kind of things we need to think about. We definitely won't have big trucks roving across an asteroid surface, but we're going to have to think about the different spacecraft that we're going to use to land on them.
So Alan, I mean, it'd be quite exciting, wouldn't it? Instead of robots, you send a person.
it would be great, as Natalie said. We know that astronauts can do a lot more than our pre-programmed or remotely controlled robotic spacecraft. But you've got to be careful. For example, Didymos, the system that HERA is going to, is a binary asteroid. And there, as the moon goes around the primary asteroid, the main asteroid, if you've got a spacecraft near there, then the gravity is going to fluctuate slightly, even though it's very weak. And so you might have difficulty controlling your craft. It's something we have to plan for with the HERA mission. So I think it would be great, but I think perhaps they ought to choose one of the 85% of near-Earth asteroids that aren't binaries, at least to start with.
Now, I've just noticed in the background of the shot there, you've got a dinosaur, which kind of reminds us of the importance of looking after asteroids, although it is being attacked by a Dalek. There. And I suppose that's the point, isn't it? It's really important to study them, and it's really important to keep an eye on them and just understand what's coming our way, as well as the science.
That's right. And again, going back to it, HERA is a planetary defense mission. That's what its goal is. That's what it's going to do. We'll get science out of it, exciting science, but what we're trying to do here is perform our first experiment on moving an asteroid. We've done all the calculations over many years. Let's put it to the test. Does it work? If it works, then perhaps in the future we can protect ourselves on this planet. If not, it's back to the drawing board.
So, Natalie, Asteroid Day 2020, what would be your message, if you like, your take-home message about asteroids?
Well, I think it's definitely about not fearing them. I think it's like they kind of have been treated for centuries as the enemy because we didn't understand them. We're always scared of our enemy if we don't understand it. So I think what it's about now is moving the science forward, trying to understand more about these objects, how they behave, what they look like, what they're made from, and how they're going to behave in the future, more importantly, so that we can prepare ourselves if one were to be headed our way. Hopefully we'd have the technology and the resources to be able to deal with it and it not to be an issue. But we also have the potential that they could offer us resources in the future to progress technologies and to save our own planet. So I think there's a lot of potential for asteroids, and I just find them really exciting objects.
Alan, what about you?
Well, as Natalie said, I think the important message from Asteroid Day 2020 is not to be overly concerned. Astronomers have made amazing progress over the past couple of decades in finding these objects and tracking them and knowing where they're going. And now we're stepping out there. We're going off to see if we can move an asteroid, should we need to do so in the future. The next few years are going to be really exciting with the DART and HERA missions, and none of us can wait really to see what they manage up there.
Professor Alan Fitzsimmons, Dr Natalie Starkey, thank you very much for joining me. And thank you very much for watching. This has been Asteroid Day 2020 from the European Space Agency. I'm Richard Hollingham. You can find out more on the website asteroidday.org. Thanks for watching.